right now. So this is I want to welcome you to chapter 8, application of derivative. Also, so now I've walked you through you know derivative, the basic or fundamental principle of differentiations. Okay, so what we want to do right now is actually to discuss application. Yeah. Okay, so let me say this. Application of derivative in real life and science. Okay, that's a very huge role. So, wow, in physics and engineering, okay, very useful in physics and engineering, particularly when you want to figure out what I call velocity and acceleration. Okay, so other out optimization in electrical circuits or even in economics and business, where we talk about elasticity of demand, we talk about marginal analysis, okay, all of that involve derivative. Okay, so even in medicine, okay, we want to talk about the rate of disease spread, or you want to talk about pharmacokinetics, or you know, here the derivative help to calculate the rate at which drugs are absorbed and eliminated in the, of course, derivative actually play a very huge role. So we want to talk about in environmental science, we want to talk about population dynamics, we want to talk about, using the idea of derivative to model the growth rate of population and how they change with environmental factors. So we want to talk about the climatic condition, and so like that, transportation, all the way to sports. Of course, derivative is actually, very, very useful. But right now, I actually want to start with how we can actually use the idea of derivative, how we can apply that, to finding the equation of the tangent or line to a given function. Okay, so as you can see what I'm displaying right now, okay, so we got a target line. Of course, this is the function. The straight line is a, yeah, you can see the f of s, maybe a curve. Okay, you can actually see a normal line, the one that is perpendicular, and of course, we also have a target line. The idea of derivative can actually be used to find the equation of the target line. Okay, to f of s. Okay. Uh, what is it? What are the steps? The steps you actually gonna follow. Number one, so finding the y coordinates of tangency. Okay, by plugging x into the function of x, and after that, you're gonna find the derivative, okay, which we call the f prime of x. So the moment you have the derivative in place, of course, we can figure out for the slope of the tangent, okay, m, okay, by plugging x into the derivative. Okay, then we substitute the slope and the coordinate of the point of tangency into the point slope equation of the line. Also, the point, the equation of the line that we actually are going to be using, okay, is going to be this guy here. Okay, so that we call y minus y1 equal m into x minus x1, okay, which can also be simplified y equal to ms plus b. Okay, we all know that to be equation of a straight line. So we got 5 steps, if you really want to figure out the equation of the target line to f of x. And we're also going to repeat the same step, so when we want to figure out the equation of the normal line, okay, we want to figure out the equation of the normal line, we are also going to follow the same steps, okay, except that we're going to substitute in the perpendicular opposite reciprocal slope, so this step as well. Now, I want to walk you through an example. So in the example, okay, want to find the equation of the tangent and normal, okay, to what you have right now. Okay, so I need you to pay attention. There is a function given, right? It is like quadratic in nature, right? and they wanted to figure out the equation of the target and the normal, okay, to that at a point where we got x equal to 2. So if you want to go by the steps, I showed you the other time, okay, what we're going to do is we need to for plug in that particular point, the value of x given into this equation. And when we do that, well, y equal to 5. So it means with the initial value of x equal to 2, the initial value of y equal to 5. That's what it means. And after that, the next thing we're going to do is we're going to differentiate this guy. Differentiating this guy now, it's going to give us this guy here. Okay? So the moment you have that, all what you're going to do is to plug in the initial value of x again, okay, into the derivative. Okay, doing that now, it's going to give us 7, right? Take a look at that. So what are we going to do? So the next thing to do is, like, if I actually want to construct or want to find the equation of the target, okay, so I'm actually going to make use of the equation that I talked about the other time. Give me 1 second. I'm actually going to talk about this guy. Okay, now y minus y1 equal to n. Of course, your x1 is given, the initial value of x is given, initial value of y. So the initial value of x is x2. The initial values of y is 5. And of course, the slope that we got is n, right? Okay, that very slope is actually 7. Okay, so what we're going to do, by the time we plug in the value of x equal to 2 and y equal to 5 and the slope of 7 into this equation, that will give you the equation, that's going to give you this, which is what we call a target line. So, but when you have your equation this way, what we're going to do, we're going to solve for that because we want it to look like a straight line. We want to put it in this standard form, a y equal to ms possible. Okay, so right now, finally, okay, that's all we got, right? Okay, so that's all we got. So give me 1 second. I'm going to clean up right now. Okay, so what we got right now is this. Okay, that is the target line that we just talked about. Now, if I want to get a normal line, okay, all what I'm just going to do is, since my slope equal to 7 here, I'm actually going to get the negative reciprocal. Yeah, the negative reciprocal of that. So if this is 7, it's going to be negative 1 over 7. So I'm going to still use that equation, but the only difference between this and this is the slope. Here I use a slope of 7, and here I'm going to use a slope of -6. So by the time I plug that in, I actually simplify that. That is going to be a normal line. Okay, so what I just found now, we just find the normal line, and we also find the target. Okay, so which are what you see, both the target line and the normal line, they are actually straight line. Look at that. Look at that. This is a normal line, and this is a target line. Okay, that's a straight line, right? That's what we just got. And of course, you can see a curve. The curve is the f of s. The question given initially, okay, which is a 3s squared minus 5s plus. That's how we do it. So the idea of derivative was actually used. Okay, so another thing that you need to understand, you need to understand some of basic fundamentals when it comes to. Okay, so how do we define if a function is increasing and with respect to slope, and when it is decreasing with respect to slope? So what I'm going to say, when a function has a positive slope, then that function is increasing. And when it has a negative slope, then it is decreasing. And another thing we can also talk about is relative maximum. Okay, relative maximum, is when relative maximum actually means if when the function changes from increasing to decreasing. Initially it started increasing and it gets to a point, it changed direction to decreasing. So we're actually gonna call that relative maximum. And of course, the relative minimum, on the other hand, when it changes from decreasing to increasing. Okay, and you know the combination of that actually we call that relative or extremer. Okay, then we can also have situation where the function could curve, could curve upward. When it curve upward, we're actually going to call that a concave. Or they call that one called downward. Actually, going to call concave down. Okay, a situation where point where it changed concavity actually called a point of inflection. And of course, you can also have a stationary point. Okay, so when you have a given function and you actually differentiate with respect to x, you set that to 0. Of course, that's going to be a stationary point. And we can also get a critical number. Okay, the critical number of f is going to be a point, where that derivative is actually equal to 0. So what I'm gonna say in conclusion about that is if the derivative of x is actually greater than 0 for all x in the interval AB, where AB is a constant, then we're gonna say f is increasing on that particular interval. And of course, the derivative is less than 0 for all x in the interval AB, then we're gonna say it's decreasing on that. Okay, so we have a first derivative test, okay, that I'm actually going to walk you through using the idea of relative maximum or relative minimum. Okay, I actually defined a relative maximum the other time when a function changes from increasing to decreasing. And of course, when that happens, the f prime of a will change from positive to negative. Don't forget, you know, positives indicate increasing, negative indicates decreasing. And of course, relative minimum on the other hand, if function changing from decreasing to, of course, the f prime of x also going to change from negative to positive. I just wanted to take note of that. Now, there's something I will call concave or concavity test. Okay, if I want to do concavity, I actually need a second derivative. So you can see here, it's a second derivative, right? If the second derivative is greater than 0 for all x in that particular interval, then we're going to say f is concave or, okay? And when it is, when second derivative is less than 0, we're actually going to say it's concave down. Okay, so which means the nature of the second derivative actually affects whether the function is going to be a concave up or down. Okay, a situation whereby the second derivative is exactly equal to 0, then we're going to call that a point of inflection. Okay, now I'm going to walk you through the example. Now, okay, so I needed to take a look at what I have. Use the derivative of f of x, this, to find the intervals on which f is increasing or decreasing, then find any relative minimum or maximums, then use the second derivative or to find the intervals where the function is concave up and concave down. And also find the inflection point. Okay, then use that information and intersect the graph. Okay, so if you we're actually gonna follow the way I explained the other time. You have this as a function, okay, and you find the first derivative, then you set that to 0. When you set that to 0, then you solve for x. So solve for x, it's gonna give you -1 and 2. Now, looking at the -1 and 2 right now, you can start plugging in all the numbers into the f prime of s, and of course, you actually are going to see, because you're going to go from -1 to 2. So you're going to start, you're going to be increasing from -2 to -1, junior 2 to infinity. Then the decreasing part, okay, is what you actually have here. Okay, so the next you're actually gonna do. So you want to know which of the two numbers here is actually gonna give you the maximum of the function, and which of the two numbers is gonna. So if you really want to investigate which of the two numbers will actually be maximum, you give a maximum value of the function or minimum value of the function. All you just need to do is to plug in, the -1 into the given function. When you plug that in, that will give you 7. Okay. And when you plug 2 in, that's going to give you negative 20. Okay, so when you take a look at that, that we enable you to see, plugging in -1 gives 7. That's a relative maximum. And plugging in 2 give negative 20. That would be relative minimum. Don't forget. You're actually going to call that minimum because the value that give us, or 2 give us the minimum, -20, and -1 give us 7. And that's why we have this classification. Okay, so after that, you want to go into the second. Since we've been able to identify your relative maximum and the relative minimum, okay, the next is how do I, you need to investigate, you find the point of inflection. And finding the point of inflection, it requires second derivative. Okay, this is the first derivative, right? Then you're going to do the second derivative. And second derivative means what I've differentiated before. I want to differentiate it again. Differentiating this guy now. I'm actually going to have this guy. Okay, so what I'm going to do now with this guy, I'm going to set that to 0, so for S, that's going to give me half. Okay, so when this guy give me half right now, okay, I actually need to start plugging in value into the derivative because, you're going to, half is between a negative, okay, if you take a look at 1/2 that I have right now. So what we're trying to say here is the way we can actually put that, we're actually going to have half to infinity, okay, up and down, okay, negative infinity to half. So it's either we actually go from half to positive infinity, or you go from negative infinity back to the half. That's what we mean. So that's exactly what. So we're going to say the inflection point now. Inflection point now is going to be 1/2 f of 1/2, then have the negative 6.5. And of course, this is how we actually going to show, you know, you sketch the graph. In sketching the graph, of course, you need to be able to know the x-intercept, and you figure out the y-intercept, okay? Then you're going to wind up having the graph. Okay, that's how to go about it. Okay, so I think I'm going to go into more application of derivative this time around in optimization problem. Of course, in optimization problem, we involve you finding the maximum or minimum, okay, values such as you're trying to maximize area, or you're trying to minimize your cost. And of course, it's better you draw, okay? You draw, you assign your variables, you write the equation that you want to optimize. Then you find the value that are sensible, okay, for the problem where the derivative equals 0. Then you verify that you have the desired maximum or minimum. Okay, so let's see how you're gonna go about that. I'm gonna walk you through it now. Okay, so currently we are on the, applying derivative in optimization problem. Take a look at this, a rectangular plot, okay, of farmland is enclosed by 180 m of fencing material on 3 sides. The fourth side of the plot is bounded by a stone wall. Find the dimensions of the plot that enclose the maximum area, then find the maximum area. Okay, so I think I said something the other time that you actually need to draw. Okay, take a look at that. You got to draw a picture, right? Now, the rectangular shape is involved. So I'm actually going to draw a picture of a rectangle. Okay, when I do that, I'm actually going to indicate a variable. Okay, I'm going to put a y, put a x. Of course, the opposite sides are going to be the same. And you all remember, the area of a rectangle is actually going to be x multiplied by y. Okay, and of course, if you take a look at the statement here, it said a rectangle plot of farmland is enclosed by 180 of fencing material on 3 sides. Okay, now when you take a look at what that means, and is that you're actually gonna have the 180. Okay, the 180, okay, it's gonna be equal to 2x plus y. Okay, take a look at, say, on 3 sides. Okay, if I'm only focusing on 3 sides, I'm only focusing on this side, this side, this side. So I'm not focusing on entire rectangle. Okay, I'm only focusing on 3 sides. And focusing on 3 sides, okay, it means x plus y. So x plus x is going to be 2x plus Also, we have that equal to 180. Okay. And you know what? If I actually have that guy, if I want to find y from here, I can say 180 minus 2x equal to y. Okay, look at that's a y, right? If I want to find the area now, I'm going to say x multiplied by y. What is my y? Okay, so my y equal to this, that's why I'm plugging that in. So I want to get my answer in terms of x. Right now, multiplying that, I'm going to have this guy. Okay, so you can see I got 180x minus 2x squared. Then the next thing is I'm going to differentiate. Okay, differentiating this guy now. Gonna give me this guy. Okay, now I'm going to, well, after differentiation, I'm going to set to 0. Don't forget that. When I set to 0, I'm actually going to solve for x. And that's going to give me 45. So the moment I get x to be 45, if I want to get my y, I can come back here. Just plug in 45 to where I got x. And I'm going to figure out y. So y is going to be 90. Okay, so x is 45, y is 90. Okay, now I can now find the area. Okay, the area is going to be 90 multiplied by 45. The area is going to be that. Okay, so that's how we apply derivative. Okay, so I want to go into another application now. So that has to do with motion. Okay, so this is the application in physics and engineering. Okay, and the four of us, have a definition, or some terms like what do we mean by position, what do we mean by velocity and acceleration. And of course, they're going to be connected or using the idea of derivative. Okay, they're going to be connected using the idea of derivative. Now, what I'm going to talk about right now is if an object is moving along a straight line, okay, then its position from an origin at any time t can be modeled, okay, by what we call s of t. It's going to be a function of t, function of time. And we call that displacement function. It's actually used in calculus. Okay, so initial position is occur when t equal to 0. So, at time equal to 0, it's not moving, right? And if you plug in t to be 0 into here, I'm actually going to have it. Now, we can actually define velocity function in terms of the distance function, in terms of the displacement function. So when I differentiate the displacement function with respect to time, that will give me velocity. And that's why we call velocity is the instantaneous rate of change of the displacement. Okay, the rate of change of the displacement is, when you have a displacement function with respect, as a function of time, and you differentiate that, that will give you the velocity at time. And of course, the moment you get your velocity, it could be positive, it could be negative, it could be 0. When the velocity is positive, of course, the object is moving to the right, or when it is negative, it is moving to the left down, to the left or down. And when it is equal to 0, the object is actually at rest. Okay? So I need to take note of that. Now, we can also, and speed is absolute value of velocity. Okay? So that is it. So we can also talk about acceleration. Okay, let me tell you this. When I differentiate the velocity, I got acceleration. I'm going to say that again. Differentiating velocity, that will give me acceleration. So differentiating velocity, don't forget I got velocity when when we differentiate the displacement. Okay, so which means if I want to get acceleration from displacement directly, I'm actually going to differentiate the displacement function twice. That's what you're seeing here. Differentiating displacement function twice will give me acceleration. And of course, acceleration at time t could be greater than 0, could be less than 0, could be equal to 0. When it is greater than 0, it is positive. It means the object is increasing. When acceleration is negative, it means it's decreasing. And when acceleration equal to 0, it is actually constant. And when the acceleration equal to 0, mean velocity is constant, and of course, it's also called minimum or maximum velocity. And of course, you also need to take note when the velocity and acceleration are the same sign, the object in motion is speeding up. Take note. When the velocity and acceleration are the same sign, Okay, not at the same sign. Maybe they are both positive, positive, or they are both negative. But situation where they got different signs, okay, the object in motion is slowing down. Okay, it's actually slowing down. Now let's go to into the application now. Don't forget, we're still on application of derivative, as it applies to motion. And of course, we actually, example is coming from field. Now, a particular moves, sorry, a particle moves in a straight line with a displacement of s meter t second after leaving a fixed point. The displacement function is given as that. You can see right now, the displacement function is a function of time. It's a cubic here, right? And of course, for t greater or equal to 0, of course, the time is non-negative. That's what it means. Now, find the velocity of the particle at any time t. Now, if you're given a displacement function at time t, you want to find the velocity, you're actually going to differentiate that. Differentiating this now is going to give me that. Okay, that's going to be velocity of the particle at time t. Now, another question said, find the initial position and initial velocity of the particle. So if you want to find the initial position, don't forget, I told you the other time, initial position, if I have S of t, okay, our initial position is at time t equal to 0. Okay, so at time t equal to 0 now, okay, so which means you need to go back out to the function, plug in 0 to wherever you say t. That's going to give you 3. And that was why we said 3 here. So our m is meter, is in meter. Where 2 is in meter. Okay, and what about velocity at time t equal to 0? We're going to do the same. You're going to plug in 0 here, wherever you see t. That's going to give you 60. Now, if you plug in 0 here, you're actually going to have 60. Okay, so that is how we find the initial position and the initial velocity of the particle. Now, if I want to find when the particle is at rest, I told you the other time, the particle is going to be at rest when velocity equals to 0. O velocity equals to 0. Okay. Now, the velocity function you got after differentiating the displacement is this. Okay, you're going to set that to 0. You're going to equate that to 0. Then you're going to solve for t. Solving for t is you actually want to know the time that the particle will be at rest. Okay, 2 and 5 seconds. Okay, you consider solving that. Now, the next question here said, find when the particle is moving left and when the particle is moving right. Okay, and of course, you actually, if you want to do that, you got 2 and 5 here, right? So you plug in values to v of t, okay, on both sides of, and that's why you have that. So what you're going to write for right, you're actually going to write 0.25 to infinity. To the left is going to be 2.5. Now, draw a motion diagram for the particle. Okay, so as you can see right now, okay, don't forget using 2 and 5. If I plug in 2 and 5 into the displacement function, okay, into the displacement function here, okay, you're actually going to have 55 meter and 28 meter. Okay, that was why the entire thing, you can see that. This is the 55 we talk about, and this is the 28 meter we talk about. And don't forget, we got 0 and 3 the other time. Okay, so take a look at that. This is a 3. Okay, and and the 0 as well. That's what we're indicating here. So now you can see here at t equal to 0, you see the arrow at t equal to 5 and t equal to 2, and that is it. Okay, so take a look at that. Okay, so I think I gave more example here. Okay, you got this displacement function, and then you're told that you already have a velocity function. Don't forget, this guy is we got this guy by differentiating the guy. So this has already been done. But the question they ask is find the average acceleration of the particle from t equal to 1 second and t equal to 4 seconds. Okay, so the average of acceleration now is going to be a change in the velocity divided by change in time. Okay, so changing the velocity, so at v equal to 1, so you come here now, you can plug in 1, okay, you come here and you plug in 4. Okay, when you plug in 1, you have 24. When you plug in 4, you got -12, changing time, and that will give you that. Okay, then after finding the average, that's how we find the average velocity, average acceleration. Okay, the average acceleration is found by using this formula. Now you want to find the instantaneous acceleration of the particle at time t equal to 3 seconds. Okay, you have to differentiate velocity to get acceleration. Whenever you add about instantaneous acceleration, it requires that we should have a acceleration. We're shading this now, that gives us this. Okay, at 3 seconds, if I plug that in, that gives me -6 meter per second square. Don't forget a meter per second square is the unit of acceleration. And the only way we can actually explain that is that, our velocity is decreasing at 6 meter per second, okay, each second at t equal to 3. That's what it means. Okay, so I think I put so many other examples. I'm actually going to do this for the displacement function from the last example where we have that, there's a meter and t greater or equal to that. We found that, of course, the velocity equal to that and the acceleration equal to that. Don't forget this guy, when you differentiate this guy, you get this guy. When you differentiate this guy, you get the acceleration at time t. Now the question says find the speed of the particle at time t equal to 3 seconds and determine whether the particle is speeding up or slowing down. Okay, now you want to get the speed, and don't forget I told you the other time, the speed is the absolute value of velocity. I'm going to say that again. Speed is the absolute value of velocity. Whether velocity is in negative or positive, the speed is still have it in positive. So if I have the velocity at t and I plug in 3 and I got a -12, if I want to get the speed, I'm going to find the absolute value. That's going to be 12 meters per second. Then I do, therefore, acceleration, I plug in 3, I got -6. And as you can see right now, the speed is 12 meters per second. The acceleration is -6. Of course, the particle is speeding up. Okay, so how do I know it's speeding up? Okay, I said something here the other time. Okay, I said something here the other time. Okay, when the velocity and acceleration are the same sign, okay, the object in motion is speeding up. Okay, when the velocity and acceleration have different sign is slowing down. Okay, so you see, acceleration -6. Okay, velocity initially -12. So they have the same sign. So when the acceleration and velocity has the same sign, the particle is speeding up. But when they have different signs, okay, speeding slowly, slowing down. Okay, okay, so that's what I have for you as far as this application derivative is concerned. So see you in next video.